The rocket. It's big, it's bold, it's beautiful, and it's also really heavy. In this rocket workshop, we're going to talk all about some of the rockets that have gone to space. We're going to talk about the rocket fuel that was used to launch them there, and we're going to do a little hands-on activity where you can make your own type of rocket at home. So let's get ready to blast off in 3, 2, and 1. Humans have been launching rockets since as early as 1926, when Robert H. Goddard made one of the first liquid-powered rockets known in existence. However, it took a while before we got rockets all the way up into space, and that was with a rocket named Sputnik. Sputnik was launched in 1957, and it was one of the first rocket ships to officially enter space. Since then, there have been plenty of notable rockets that have been built and launched for different missions with different destinations and different purposes. Some of those include the Saturn V rocket. The Saturn V rocket was one of the largest rockets ever built by humans, and it was what we used to get astronauts to the moon in the Apollo missions. The Space Shuttle rocket was also a large rocket used to transport astronauts from Earth all the way up to the International Space Station. The Space Shuttle missions launched from 1981 all the way until 2011. And after that, they started to use the Soyuz rocket, which was a Russian-built rocket that gets astronauts from Earth up to the International Space Station and is what is currently used. This year, in 2020, we also saw the emergence of a new rocket called the Falcon 9, which was created in a partnership with SpaceX and NASA. This was one of the first reusable rockets ever built, meaning that it can be used multiple times before it must be retired. And it was also used to launch American astronauts off of American soil for the first time in over 9 years. So American space travel is beginning to re-emerge as its own industry. Because there have been so many different types of rocket ships sent into space, they're not all doing the exact same mission. Some of them have different destinations, some of them are built with a different purpose. Oftentimes they're carrying equipment or materials, sometimes they're carrying satellites, sometimes they're carrying animals, and occasionally they're actually carrying astronauts. With each rocket launch and its specific mission, a rocket may contain different pieces and parts that make up the entire thing. But overall, rockets tend to have similar anatomical features or pieces and parts that allow them to actually fly and move through the air in the most efficient way possible. That makes them the most aerodynamic. That kind of means the ability to fly and to cut through air. We're going to look at the different pieces and parts of rocket ships by using one of my personal favorites, the Saturn V. We're going to break down the anatomy of a rocket, looking at its different pieces and parts, using this model of the Saturn V. Now remember, the Saturn V was one of the largest rockets ever launched into space. It weighed over 6 million pounds, and it was the rocket ship that was used to get astronauts to moon and back in the Apollo missions, which were in the 1960s. That's a long time ago. That's over 50 years ago. That's maybe older than some of your parents and maybe older than some of your grandparents. So rockets are built to be what's called aerodynamic. That means that they can slice through the air very quickly and efficiently. In order to build a rocket, there are many different pieces and parts. And oftentimes rockets are built in specific sections called stages. Stages are the parts of the rocket that maybe fall off or break apart, and they're built separately before the rocket is assembled and then ready for launch. The main part of the rocket is called the body. The body of the rocket is this generally main section, and the body can contain everything that goes inside of it. Almost all rockets also have rocket boosters, and these can be found on the bottom of the rocket ship. Now, they can have anywhere from 3 to 5 boosters, maybe more, maybe less. And these boosters are where the rocket fuel burns and the energy shoots out of. Because these rocket boosters are on the bottom, this allows for the energy to shoot down and in return send the rocket upwards into space. In order to keep the rocket on track and stabilized as it's hurtling through the air, rockets will also sometimes have what are called fins. And fins are these flat pieces connected to the sides of the rocket. These fins can help as the air is going over the rocket to break the air apart and keep the rocket from shaking or turning in a direction it does not want to go. All the way up on the top of the rocket is where you might find something called an escape pod or an escape tower. Now, the escape pod or tower is there in case of an emergency, in case something goes wrong. If needed, it can break apart from the rocket ship and can fall back to Earth safely with the astronauts or the equipment inside of it, so that if anything were to go wrong, nothing would happen to the people on board. Underneath the escape tower is typically what we call a nose cone. And a nose cone is called what it's called because it's on the top and it looks like a cone. And this can help slice through the air as the rocket is traveling. It wouldn't be as efficient if a rocket had a flat top, because that might not cut through the air as quickly as it needs to be, and that means you would need more fuel and more power to get it where it needs to go. Within the actual rocket ship is something called a payload, and a payload is typically the equipment that's on board. This could be the satellite or the rover or even the astronauts that are sitting inside and that are being delivered to a different location in space. Lastly, many of the rocket ships, especially those today, are built with really advanced computer systems. These are systems that can operate with or without humans that can help steer the rocket ship, make sure it's not crashing, but also communicate back to Earth what its status is and how it's doing. This is really important when we're launching something like rovers, where there cannot be humans on board because they're going very far distances to places like Mars. Now, each rocket is a little bit different depending on its mission and depending on what it has on board, but in general, the body, the nose cone, the fins, that's kind of what you need to make a rocket. And then, of course, the rocket boosters. So all of these pieces and parts, they sure do add up. And that makes rockets weigh a lot. In fact, rockets can weigh anywhere from 4,000 to 6 million pounds, which is really, really heavy, especially when the goal is to get these rockets off of planet Earth and into space. So scientists need to think of ways to actually fight against the gravity that's pulling these rockets down, that's causing them to weigh 6 million pounds, and to suddenly make them feel weightless so that they can fly and fly and fly. So to launch rockets into space, we need to create a specific type of motion called thrust. Thrust is defined as when a system expels or accelerates mass in one direction, the accelerated mass will cause a force of equal magnitude but opposite direction on that system. Super fun. In other words, thrust is creating enough energy in one direction that the object we're talking about goes in the opposite direction. Similar to a balloon. A balloon is a really good example of how we can create thrust. In order to create thrust, we have to have energy or motion pushing something in the opposite direction. So instead of fuel, we're going to use a special type of fuel, air. As I push air into this balloon, I'm adding air molecules. Air molecules are invisible to the eye, but we can see that they're putting pressure on the balloon. They're actually filling it up, they're stretching it out, and they're trying to escape. They're bouncing around in there, filling it up with potential energy. And the more air that I add, the more potential energy I'm putting into this balloon. So we can imagine that this balloon right now is filled with fuel, similar to a rocket being filled with rocket fuel. But I'm not letting it escape. However, if I were to finally release the end of this balloon, all of this potential energy inside of this balloon would then move and turn into kinetic energy. Now, if I were to release the end of this balloon, point in the direction that you think the air molecules that are currently inside would go. Yeah, these air molecules would go out that way, out of the end, and in return, which direction do you think this balloon would go? That way, the opposite direction. So a force going out in one direction causes enough energy and motion to take the object and send it in the opposite direction. This is thrust. The same concept can be applied to a rocket. However, instead of air, rockets have to use much more powerful fuel because rockets don't weigh as little as a balloon. Remember, they weigh millions of pounds. To get a rocket up into space, they need to create enough energy and force coming out of one direction, the bottom of the rocket boosters, to send the rocket in the opposite direction, up towards the sky. This takes a powerful explosion, or what we call combustion. And to create this, scientists need to burn very flammable objects, things called rocket fuel. Now we're gonna watch a short video clip of an actual rocket launch, of a space shuttle launch. And in this clip, I want you to pay close attention to what you're noticing. What do you think their rocket fuel might be? And how do you think this rocket fuel is burning? And how is that energy actually getting the rocket up into space? So just pay close attention to the things that you notice and the observations that you're making, because this is a real rocket launch and it will show you exactly how this works.
Firing chain is armed. Sound suppression water system activated. T-minus 10, 9, 8, 7, 6, 5, 3, 2, 1, 0, and liftoff of Space Shuttle Atlantis on a mission to build, resupply, and to do research on the International Space Station.
Houston now controlling. Atlantis begins its penultimate journey to shore up the International Space Station. Atlantis now in the proper alignment for its 8.5-minute ride to orbit, 4.5 million pounds of hardware and humans taking aim on the International Outpost. 30 seconds into the flight, Atlantis almost 2 miles in altitude, almost 6 miles downrange from the Kennedy Space Center already, traveling 500 miles an hour. Booster officer confirms staging a good solid rocket booster separation. Guidance now converging. Atlantis steering into the center lane of Highway 129 en route to the International Space Station.
What did you notice in that rocket launch? Go ahead and talk to someone next to you, or tell your partner, or tell a friend, maybe some of the observations that you made of this rocket launch. You may have noticed all of the flames and the fire that was coming out of the bottom of the rocket. You may have noticed all of the smoke happening as well, and that's a side effect of all of that burning fuel. You may have noticed the sparks that were used to ignite it. You may have noticed the sound, that it sounded really loud, and you may have noticed that the camera was shaking, which means there was a lot of power and movement. And that's exactly what rockets need. They need a big giant explosion out of the bottom so that the rocket can go up to the top. When scientists build rockets, they can choose between pretty much 2 different types of rocket fuel, either solid fuel or liquid fuel. Now we're gonna do some demonstrations to explore how solid and liquid fuels burn and compare them to figure out why a rocket ship might use solid fuel or liquid fuel or a combination of both. So get ready, because these are about to be some explosive demonstrations. The first kind of fuel that we're gonna look at is solid fuel. And what we're gonna use to represent solid fuel and to understand how it burns is this. This is a powder called lycopodium powder. It's made from a type of moss that's dried and ground up into this really fine dust. Now, lycopodium powder, because it's made of organic materials, like a plant, that makes it really flammable. And that means it can be great for combustion. To be flammable means it can light on fire. So essentially, if I were to light a match and drop it into this lycopodium powder, it should light on fire, right? Like rocket fuel, right? Let's find out. We have our fuel, which is lycopodium powder, and in order to get it to light on fire, we should add a spark. So let's take this match and drop it in 5, 4, 3, 2, 1. Excuse me? Let's try that again. 5, 4, 3, 2, and 1. Our lycopodium powder is not lighting on fire. So we have our lycopodium powder, which is supposed to be our solid rocket fuel, and we dropped 2 matches into it and neither one of them lit. So I think there's something missing in this reaction, but I'm not sure exactly what. Do you think you know what could be missing in this reaction in order to get combustion to happen? If you think so, tell someone next to you. What do you think we're missing? Those are some good ideas, but I think I have an idea as well. Let's see. So I'm gonna try this again, but a little bit differently. Rather than taking a match and dropping it into lycopodium powder, I'm gonna take the lycopodium powder and pass it by a match. So I'm gonna take some, and I'm gonna siphon it using the siphon, and I'm gonna put it into this big tube. And at the end of this tube, what do you notice I have? We've got a lighter. So I'm gonna take some of my fuel, and I'm gonna pack it into my tube. Now what I'm gonna try doing this time is I'm gonna blow on this tube, one big nice breath like this. And we're gonna see, as this lycopodium powder travels through the tube and past the end of this flame, if we can get a different type of reaction to happen. If you think you have a prediction of what might happen, tell someone next to you while I get ready, okay? Make a prediction now. All right, hopefully you've made a prediction. Are you ready to see what happens? But I need a countdown, just like every good rocket launch. So, count me down in 5, 4, 3, 2. Whoa! Did you see that? That was pretty cool. That was much more rocket fuel-y. Don't you agree? Are you ready to see it again? In 5, 4, 3, 2, 1. Whoa! Now, how long did that last? Tell someone next to you. Was it 1 second, 2 seconds, 3 seconds? I don't know. I needed your help to figure that out. So turn to someone next to you and tell them how long you thought that reaction just lasted. Now, what did you notice was the difference between when I lit a match and dropped it into lycopodium powder and when I did it like this? The biggest difference was that I blew into this and I added some air. In order for combustion to actually occur, there has to be oxygen present. If there's no oxygen present, a fire won't actually burn. So rocket ships have to find a way to oxidize their fuel, just like we oxidized our fuel right now. Now, it wasn't the oxygen from my breath that was allowing this lycopodium powder to combust, but rather, as I blew air into this tube, that pushed the particles of the lycopodium powder past the spark and into the air, and it suspended each individual particle in the air, and there's oxygen in the air. So because each particle could be surrounded by oxygen, that allows the fire and the combustion reaction to occur. Bigger, better, all at once in this explosive manner. So rockets have to figure out how to get oxygen into their fuel source, just like we did with our solid fuel today. Unfortunately, rockets are not powered by lycopodium powder, but instead they use different types of solid fuel. There's a few different examples. The first type of solid fuel ever used was actually gunpowder, and it was used to launch fireworks. There's also solid fuels that can be used for model rockets. Those are smaller rockets not used for space travel, and they like to use things like zinc sulfur propellants. When it comes to big giant rockets, like NASA-sized rockets, they use something called ammonium perchlorate-based propellants, or APCPs for short. Now, solid fuel is really great, but as you noticed, it burns fairly quickly. Even in our lycopodium powder reaction, it only burned for about 1 to 2 seconds. That means if you want to launch a rocket with solid fuel, you have to have a lot of solid fuel, because once you light it, it burns. It burns all at once. And you're going to need a lot of fuel if you want it to keep burning from the time it leaves Earth to the time that it reaches space. Even though solid fuel creates this big, powerful explosion, enough to create the thrust that a rocket needs to get to space, they need a lot of fuel to keep that thrust going until you actually reach your destination. That's one of the benefits of solid fuel, is that it's very powerful, but one of the drawbacks is that you need a lot of it. And this leads us to our next type of fuel that we're going to explore, which is liquid fuel. The second type of fuel that can be used to power rockets is liquid fuel. Now, liquid fuel is a little bit different than solid fuel because, first of all, it's a liquid. There's a difference between liquids and solids, similar to how there's a difference between ice and water. The type of fuel we're going to use to show how liquid fuels burn today is isopropyl alcohol. Isopropyl alcohol is a clear liquid, and it almost looks like water. And it's the kind of stuff that you can use to put on your cuts if you have a cut, and you can find it in the grocery store. But isopropyl alcohol, just like lycopodium powder, is extremely flammable. And you should never play with isopropyl alcohol and lighting it on fire at home, because it can be extremely dangerous. But for the sake of showing how liquid fuel can burn, we're going to use it today and light a little bit of it on fire. So to understand how liquid fuel burns, I'm going to take a little bit and pour it into this glass beaker. Now, I just poured a tiny bit, barely enough to cover this. But if I were to take this glass beaker with a little bit of isopropyl alcohol and light it on fire, it is flammable, so what do you expect to happen? It should light on fire. So let's find out. Now, you might not be able to see this flame very well, but you should be able to see at least some flames. So what's happening is that this isopropyl alcohol fuel, this liquid fuel, is burning. And it's going to burn nice, low, and slow until it burns all the way out. Now this is a little bit different than the lycopodium powder because look at how long this reaction is taking. It's been 5 seconds, 10 seconds, maybe even longer. But this type of reaction is not very powerful. It's not enough energy created to create the thrust needed to get a rocket all the way into space. So if we're going to take liquid fuel and turn it into rocket power, we need to do something different to it. What I need to create is something called a whoosh bottle. Now, to create a whoosh bottle, I need a bottle. I also need my liquid fuel. Not very much. And I pour it into my bottle. What I then do is put this white cap on the top and spin it around. Now, while I'm spinning it around, the fuel that is inside of here, reminder that liquid fuel, is starting to transform. Now, if you think you have an idea of what's happening to this liquid fuel, go ahead and tell someone next to you. What's happening is the liquid fuel is coating the sides of this bottle. And as it does so, this liquid fuel transforms and it vaporizes. What that means is that the liquid is turning into a gas. It's the same thing that happens when you see a puddle of water on the ground on a hot day. That water, all of those water molecules, they heat up. And as they heat up, they change form. They change states of matter from liquid molecules into gas molecules. And they evaporate into the air. You might come back later to find that that puddle is gone. Now, because I have a cap on this jug, I'm keeping all of this evaporated fuel inside the jug. That means this is filling slowly with flammable fuel and it should be very highly combustible. The next thing to do is to light it on fire. But before I do that, I want you to make a prediction of what you think is going to happen and how this fuel is going to burn. Go ahead and make a prediction now. All right, have you made a prediction? Are you ready to see what happens? First, I need to get my spark, because as we've learned earlier, combustion needs a spark. We also learned that combustion needs oxygen, and inside of my jug right now should be a lot of oxygen. In order to get combustion to happen, we need to combine our spark with our oxygenated fuel. So let's do it in 5, 4, 3, 2, 1. Oh, that was pretty sweet. What did you notice? Go ahead and take a minute and tell somebody next to you an observation that you made about this whoosh bottle reaction. Ready, go. So we're going to complete that reaction again. This time, I want you to pay close attention to how quickly this reaction happens, just like we did with the lycopodium powder. I want you to pay attention to the amount of energy and the amount of force that you think could be created by using liquid fuel, and I want you to try to compare it to the solid fuel that we burned earlier. I also want you to pay close attention to the observations that you make. Where does the energy go when we light it on fire? All right, friends, just like every good rocket launch, I'm gonna need your countdown once again. In 5, 4, 3, 2, and 1. We could launch some rockets with this. Go ahead and share with somebody next to you the observations that you made. How long did that reaction actually take? Was it 1 second, 2 seconds? How was it different from when we burned solid fuel to when we used liquid fuel? Think about it and share with somebody next to you. During our whoosh bottle, you may have noticed several different things. First of all, you may have noticed that the flames traveled down the side of the bottle and danced along at the bottom. You may have also noticed that their color was a little bit different than regular fire. It was kind of yellow and kind of orange, but also kind of blue. And another really important observation you may have made was that the flames were shooting out of the top of the bottle. And this has implications for how a rocket fuel engine would work, because all of the energy was released out of the top. And that means the opposite energy and motion would be pushing down towards the bottom. If I were to take this bottle and actually turn it upside down, the energy from the combustion would begin to shoot out of the bottom of the bottle, which means the rest of the bottle would be sent straight up into the sky. This is exactly how rocket engines work, where this would be the booster and this would be the nose cone, and if the reaction was big enough, it creates that thrust that's needed to get the rocket off ground into space. When we vaporize liquid fuel in the same way that we just did, we can create much more powerful combustion reactions. We can create a lot more energy, a lot more explosivity, and this can help launch rockets into space. Rather than just burning liquid fuel in its liquid form, many rocket engines have a vaporizing technique where they can turn their liquid fuel into a vapor so that it fills the entire rocket engine. Then they can light that flammable engine filled with flammable gas on fire, and it creates a big enough explosion that it can launch the rocket into space. Now, rockets aren't launched using isopropyl alcohol. They have to use much more powerful types of rocket fuel. This is just an example to show how liquid fuel can burn and can be used to create combustion. Some examples of liquid fuel that rockets have actually used includes liquid oxygen in gasoline, liquid oxygen in kerosene, and even liquid hydrogen, which is one of the most common types of liquid fuel used to launch rockets today. If we wanted to try to do our own rocket launch, maybe using the same concept as a whoosh bottle. Do you think we could? Remember, if we were to just point this upside down, essentially the energy would shoot out of the bottom and the bottle should travel up towards the sky, like a rocket. So maybe we can do that, but maybe at a smaller scale. So what I'm gonna do is I'm gonna take some of this isopropyl alcohol, the same fuel that we used in our whoosh bottle, and I'm gonna add some into a smaller bottle. Instead of our whoosh bottle, we'll do it at a smaller scale. And just like with the whoosh bottle, I'm gonna put the cap on, and I'm gonna vaporize this liquid fuel inside of my bottle. To vaporize it, I'm gonna shake it around, spin it, make sure it's coating the sides, and make sure that that liquid fuel is turning into a gas, filling the inside of the bottle. Our bottle right now should be filling with vaporized fuel, vaporized flammable gas that we can hopefully use to launch it. To launch it, we're gonna need something like a spark. And we have a special tool, and this is a home-built sparker. It's a barbecue sparker. At the end, we have these two little pieces that when we press the button, they make a small spark. So we have our fuel, it's oxidized, we have a spark. Let's see if we can make some combustion happen. All right, we're launching in 5, 4, 3, 2, 1. This is a great way to show how rockets not only use fuel that's vaporized, but to show that same concept we've been talking about over and over again, that thing called thrust. As we burn the fuel inside of our bottle, well, the energy goes which way? Point to it. Yeah, the energy goes down, and the bottle itself moves in the opposite direction, which is up. If I were to turn it this way, which way would the bottle go? If I were to turn it this way, which way would the bottle fly? If I were to turn it this way, which way would it fly? Exactly. The energy going out of one direction pushes the object in the opposite direction at an equal force. So this is one really fun way to show how rocket engines can use fuel to launch into space. Now, unfortunately, we do not recommend that you try this exact experiment at home. However, we do have a different hands-on activity where you can craft your own rocket and add some features and test them out using some simple objects that you may find around your house. So grab your materials and then let's get ready to get our hands on some rockets. Woo! In order to make these rockets at home, you're going to need a few different materials that you might be able to find. Those materials include balloons, any size or shape, or you can get a mix of sizes and shapes and try different ones. String. You're going to want enough string that you can reach from one wall to another in your room, in your house, or in the place that you're at. Tape, enough tape to go around. Straws, enough for everyone in your group to have at least one straw. Something to fill your balloons with if you need it, like an air pump. Scissors for cutting, scratch paper that you may be able to use to cut up, markers, crayons, or any other drawing utensils that you may want to use. Now, once you have all your materials together, you can follow the instructions step by step that we're gonna go through next. Because what we're gonna make today are balloon rockets. We're gonna use the concept of thrust, and we're gonna make some rockets of our own that can go from one side of our room to the other. We're gonna test out to see if we can change the way our rocket flies based on how much fuel we use, the shape of our rocket, the way we put our fins and our nose cone on our rocket. We may even be able to design things like second or third stages onto your balloon rockets. Now, this is all going to be looking into the concept of thrust and aerodynamics, and it's a super easy way to do it. So follow along with these steps, and we're gonna make some awesome balloon rockets. The first step in our balloon rocket activity is to determine your mission pathway, where your balloon was going to start and where its destination is. What that means is you want to take your string and you want to determine where you're going to put your string in your room. And you want to tape one end to one wall and one end on the other wall. This is going to determine the pathway or the flight path of your rocket as it goes from one place to the other during launch. Once you've figured out where your string is going to end, you can cut it. And on this end, you're going to take one of your straws and slide it over. This part can be kind of tricky, but you want to put your straw over your string or your string through your straw and find a way to guide it through. So what you end up with is your string, one side is taped to the far wall, and then you have your straw through your string on the other side. This is going to be what we're going to attach our balloon rockets to, and it's how it's going to slide easily from one way to the other. Now you want to select your balloon, and you can do different size balloons or different shaped balloons, but for now, pick your balloon. This is going to be your rocket. Just like in the beginning, we need to fill our rocket with fuel, and in this case, our fuel is air. You can use your mouth to add air, or you can use a pump like me. Once your balloon is filled with air, you can try to find a way to tie it off. You can use something like a clip if you need to, or you can use your hands to hang onto it, or a string, or do a light tie. So now you have your rocket, and it's filled with fuel. But in order to get it to fly, we might need to add some other things. Remember how rockets have different pieces and parts, so now it's up to you. You can design your rocket how you want. You can use your paper and cut out pieces of paper to add fins onto your rocket. You can decide how many fins you want to add. You can also add a nose cone if you'd like to. And I want you to think about, while you're designing your rocket, the way it's going to fly. So depending on its shape and depending on how much fuel it has, which direction do you think it's going to fly when you let it go? How do you think it's going to fly when it's attached to this string, which is your pathway of your rocket ship? So consider the ways that it may or may not be aerodynamic as your fuel is pushing your rocket towards your destination. But for now, take a minute and decide and design the fins or nose cone or even the coloration on your rocket. This is up for you to personalize and make it your own. Now that you're done designing your very own balloon rocket, now you have to get it ready by putting it on the launch pad. So to do that, you're going to find the straw that you attach to your string, and you're going to decide where to attach it to your rocket. Now this is also up to you. You can decide if you want to attach it closer towards the back, the middle, or the front, which can all have an effect on how it flies. So this is up to you to explore how it's going to fly depending on where you attach it. But for now, you can attach it to your rocket by holding it up against it and then taking tape and just placing it gently over the top. If you want to reuse your rocket, make sure to put this tape on gently, because when you pull it off later, it can lead to holes in your balloon. So just a gentle stick is all you need. Once you have your rocket ready to go on its launch pad, pointing in the right direction of its destination for its mission, now's a great time to test it. So you can either, if you had your rocket pinched, you can let go of the clip, or if you were holding it closed this whole time, you can gently untie it, and you can watch how your rocket flies. Now pay close attention of how it flies, because it's going to be up to you to figure out what you could do differently to make it fly faster, smoother, or the way you'd like for it to fly in general. So let's see how I did with my rocket launch. We're ready. Let's do this. And 3, 2, 1. Oh, we did not reach our destination. We only got about halfway. So our rocket almost made it all the way to the destination, which was the end of the wall. It got caught right about here. Oh, there it goes. So now it's time to take part in the engineering process. You've already made one design of a rocket, and you've already tested it once. But what can you do differently? Take a minute and think or discuss with your group. What are some things that worked on your rocket design, and what are some things that could be improved? Were you happy with the way you designed your nose cone? Or what about your fins? Could you add more fins or less fins? Could you make your nose cone better? How else could you tape your balloon to your straw to get it to fly faster, smoother, or all the way to your destination? Could you use a different shaped balloon instead of the one that you used? These are some really good questions to ask yourself while you go back through and try to improve your rocket design. Go ahead and take a few minutes and work with your group or work by yourself to improve your rocket design so that it can fly more like the way you were hoping that it would. This is all part of the engineering process. We designed, we tested, and now we look at what could be improved and what worked well, and we redesign and we retest again. Once you've made any improvements to your rockets that you would like to make, you can set it back up onto your launch pad, your straw, and launch them again. If you have a large group doing this activity, you can set up multiple strings at a time so you can have multiple rocket launches happening at once. You can have races, you can have teams work together to build their rockets, and basically you can continue doing this process of designing, testing, redesigning, and retesting as many times as you'd like to. In the end, all you're working with is the concept of thrust and aerodynamics when designing your rockets. And you can use some of the information that you learned in the beginning of this video to help you make some good choices about how you make your design. And we're ready to launch. 5, 4, 3, 2, 1. Woohoo! We made it all the way to our destination! Look at that. Just a little bit of tweaks here and there, and we can make our rockets fly all the way to where they need to go, out into space. Once you're done doing your hands-on activity of making balloon rockets, you can have a quick discussion to talk about the engineering process. What kind of designs worked well, and what kind of designs could be improved? You can also discuss the similarities and the differences between the rockets that you built today and the rockets that have actually been launched to space, because they are very different things, even though they are showing similar concepts. Throughout our workshop today, we talked about some of the types of rockets that have been launched into space, the fuel that it takes to get them there, and we left you with a hands-on activity to do with your group on your own. We hope that you had lots of fun joining us here at Chabot Space and Science Center. We always encourage you to have fun with learning, and hopefully you learned a few things today. Now, we'll see you next time when we're ready to blast off again. But for now, we'll see you in 3, 2, and 1.